Advanced Placement Chemistry. This is the very first lesson of the class. It's Unit 1 Foundations, and it's lesson number 1, Math for Chemistry. So we're going to start off with some basic math functions that you'll need for chemistry. Chemistry is not all about math, but it's probably 50-50, math and verbal. We're going to talk about fractions in particular because that's generally decimals. Most things you can do on a calculator. Fractions you tend to have to do on paper, so you need to know the principles of fractions. So we'll start off with some basic principles of fractions. So to add or subtract fractions, you use the crossing arrows method, and what you need is what's called a common denominator. So what you do is take the denominator, the bottom part of one fraction, and go over to the other side and multiply top and bottom of the other fraction by that. And then you take in the denominator of the other fraction, that in this case would be the 3, and you go over and multiply the top and bottom by that. And what you'll end up with is 4/6 plus 3/6. So what you've done is created a common denominator. So if you're not sure if that's valid to be able to do that, if you're wondering, does 4/6, you had 2/3 plus 1/2, you now have 4/6 plus 3/6. Is that really valid? Well, just realize that 2 over 2 is equal to 1. And 2/3 times 1 equals 2/3. 3 over 3 is equal to 1. 1/2 times 1 is 1/2. It doesn't change the value of it. What you've simply done is given both a common denominator. So now what you do is you add the numerator, the top of the fraction, so that you have 7 over 6. All right, and that's how you would add two fractions. Subtraction is done the same way. Take the 3, multiply the top and bottom of 3/5 by that. Take the 5, multiply the top and bottom of 1/3 by that. And what you end up with is 9/15 minus 5/15. You can now subtract the numerator, the top, leave the denominator alone, leave it as it is. And there it is, 4/15. Multiplication of fractions is what you do to multiply fractions is you multiply the numerator, the top, and the denominator, the bottom, straight across. So 2 times 4 is 8, and 3 times 5 is 15, and that gives you 8 over 15. So in this case, you do deal with the denominator. Sometimes students get this confused with proportions where they cross multiply. You don't cross multiply when you multiply a fraction. Proportion is different. We'll talk about that at a later time. So it's 2 times 4 is 8, both things on the top, both things on the bottom. 3 times 5 is 15. Okay, the bottom one. Now what you might want to do is cancel before you do the multiplication. That will simplify the numbers so you don't end up with some big numbers in the answer and then have to reduce. So here we're going to simplify. 3 goes into 3 one time and goes into 9 3 times. So we've changed 3/9 to 1 over 3. You can cancel across a times sign, across a multiplication sign. You cannot cancel across a division sign, an addition sign, or a subtraction sign, only across a multiplication sign. Now you see the 4 and the 8 will cancel as well. 4 goes into 4 one time, and 4 goes into 8 two times. So now you've reduced both of those fractions down, and now you can multiply straight across. 1 times 1, 1/2 times 2 times 1/3, and that's 1 times 1 is 1, and 2 times 3 is 6. So that's how you multiply fractions. Now if you have one fraction and one integer, what you do is you simply turn the integer into a fraction by placing a 1 underneath it. So here we would have 2/3 times 4 becomes 2/3 times 4 over 1. And now you multiply across the top, and you get 8, and then you multiply across the bottom. 3 times 1 gives you 3. When the numerator is larger than the denominator, as it is here, it's called an improper fraction. You can convert that into a mixed fraction. You don't need to, as far as I'm concerned, most of the time, but it can be done. We'll talk about that in just a minute. So convert improper fraction to a mixed fraction. So an improper fraction has a numerator larger than the denominator. So 5/3 is an improper fraction. So how do you convert that into a mixed fraction? You simply do a division problem, and whatever the remainder is, you place that over the divisor. So let's see how that works. 3 divided into 5 goes one time. 1 times 3 is 3. So now you subtract. 5 minus 3 is 2. So now you're done. You can't divide any further. You have a remainder of 2. So what you do is you write it as 1, the number up on the top, and 2/3. So the remainder 2 over the divisor 3. So 1 and 2/3. So so place the remainder over the divisor. So that's how you would convert an improper fraction into a mixed fraction. Mixed means it has an integer part and it has a fraction part. Okay, how about this? Convert a mixed to an improper fraction. So let's take 1 and 2/3. How do you convert that? What you do is you multiply the denominator times the whole number that's out in front, 3 times 1 in this case. You add the number on top, the numerator, and then you place it all over 3. So you kind of go around in a loop like that. So it's 3 times 1 plus 2 over 3. And that would give you 5/3. Okay, division of fractions and integers. So what you do is, you may have learned this in different ways. You flip the bottom fraction and multiply. Some of you learned keep, change, flip. Some of you learned invert and multiply. But anyway, it's all the same thing. All right, so 2/5 divided by 4/7. So what you do is you take the 4/7 and flip it over to make the reciprocal of 4/7. So 2/5 times 7/4, and now you can do some simplifying or not. Here I didn't. So 2 times 7 is 14, 5 times 4 is 20. Now you can reduce that, and you must reduce that down actually. Reduce any fraction that can be reduced down. So that gives you 7 over 10. For integers, place a 1 under the integer to create a fraction, then flip the bottom and multiply. So here we have 2/3, the fraction 2/3 divided by the whole number 4. So we're first going to put a 1 underneath the 4 to turn it into a fraction. And now we're going to flip and multiply. So you flip the 4 over 1 to 1 over 4 and you multiply. So 2 times 1 is 2, 3 times 4 is 12, that's 2/12, and that reduces to 1/6. Here it's the same thing, except we have the whole number on top. It doesn't matter. So you make it 6 over 1 divided by 2/5. You flip the 2/5 to become 5/2. And that's 6 times 5 is 30, 1 times 2 is 2, 30 divided by 2 gives you 15. Units of measure are essential in chemistry and other sciences. Units of measure are the word or abbreviation that comes after the number to indicate what you're dealing with. So if I say to you, do you want 10? The obvious question you would ask is, 10 what? 10 pizzas? 10 books? What are we talking about? So in this example, pizzas and books are the unit of measure. They indicate what the number, to what the number is referring. So units of measure can be canceled in the same way as numbers or variables, and this is going to be really a centerpiece of doing chemistry, is the ability to do this. So treat numbers and units that are not in fraction form as though they are in the numerator. Okay, so here you have 3 moles per liter. That's a unit of measure we'll learn about later in this class in a few weeks. And then you multiply it by 4 liters. Now the 4 liters is just, it doesn't have a numerator denominator to it, so you treat it as though it's in the numerator. If it just is on one level like that, you treat those liters like they're up on top in the numerator. So what you can do is, you can just put a 1 underneath it. So 3 moles over 1 liter, because that's what 3 moles per liter means. 3 moles over 1 liter, and again, you'll learn what moles are later, it's just a unit of measure right now, times 4 liters over 1. So what you see is you have a numerator and denominator for both of those now. You can make the liters cancel out, just like you made numbers cancel out in the previous slides. You can make units of measure cancel out. And then you still have 1 unit left, and that's mole. Whatever you have left after you're done canceling all the units that can be canceled, that's what's going to be the unit for your final answer. So now you can go ahead and do the math. So 3 times 4 is 12. The unit you have left is mole on the top, so it's 12 moles. For integers, place a 1 underneath the integer to create a fraction, then flip the bottom and multiply. So we saw that before with numbers. Okay, so this one's a little more complicated. 12 moles over 2 moles per liter. So what we're going to do first is turn the 12 moles into a fraction, 12 moles over 1 liter, and then you're going to adjust the bottom one, the 2 moles per liter, you're going to change it to 2 moles over 1 liter. That's what 2 moles per liter would mean. And notice that you don't really even have to know what a mole is to do this. It's just understanding the principle of how do you do these cancellations. Okay, so now we flip the bottom. So we have 12 moles over 1 times 1 liter over 2 moles. We flip the bottom. So now you can see that moles are going to cancel across that time sign there like that. So now the only unit of measure we have left is liter. And so now it's what you do is multiply everything on the top and divide by everything on the bottom. So on your calculator, what you would type in is 12 times 1 divided by 1 divided by 2. Multiply everything on the top, divide everything on the bottom. And what we get there is 12 over 2 is 6 liters. That would be your final answer there. This skill is central. That's why we're hitting it on the very first day, this ability to cancel units of measure. Believe me, you'll get plenty of practice at it, so don't worry. This will be something that we really focus on in this class. Okay, now we're going to solve a problem. How many centimeters in 4.5 meters? So to make this conversion, you must know the relationship between centimeters and meters. Some of you might know that already. But when we do these problems, you will always be given the relationship. There are 100 centimeters in 1 meter. And that's called an equivalency. 100 centimeters equals 1 meter. That can be expressed in 2 different ratios. There's 1 meter for every 100 centimeters, or there's 100 centimeters for every 1 meter. Those are both true statements, and those ratios are called conversion factors. Now you may say, wait a minute, in math you can't just say 1 over 100 is the same as 100 over 1. Those are totally different numbers. But here you have actually a unit attached to the number. It gives it an actual meaning. So 1 meter, it's a specific relationship between 1 meter and 100 centimeters. It's not just a number 1 and the number 100. So because you have units of measure attached, you can say that both of these are valid statements. They're both true statements. By the way, there's a word that we use per, P-E-R, which means for every. So you could read this 1 meter per 100 centimeters or 100 centimeters per 1 meter. And those are called conversion factors. So the conversion factors are 1 meter per 100 centimeters or 100 centimeters per 1 meter. So this is read just the way I said it, or you could use for every. There is 1 meter for every 100 centimeters, or there are 100 centimeters for every 1 meter. That's the way you would read those ratios. These are both true statements, so we need to choose which one which one we need to go into the equation to figure out how many centimeters in 4.5 meters. So let's go ahead and solve this problem. In solving this problem, the first thing you want to do is identify what is the question asking for. You always need to identify that right away. When you leave your house in the morning, you don't just go out and wander around. You have a destination in mind. You know where you're trying to get. And the same thing here. We have to know what we're trying to get to. So in this case, you begin with what you're looking for. In this problem, it is the number of centimeters, cm. So you write that way over on the right side of your page, because that's where your answer is going to be. We're going to set up an equation here, and your answer, as it usually does when you write an equation, comes over on the right side. Now, what are we given? Think about it. What are you given to start with? Okay. So you're given 4.5 meters. And we always use the abbreviations, and we'll talk about the abbreviations for various units of measure in just a short while. So you identify what you're given. In this problem, it's 4.5 meters, which we abbreviate with M. And this is the value. This value is in the numerator. In other words, remember, if there's only one level to it, it's considered to be in the numerator. You could imagine there's a 1 down below it, 4.5 over 1, but you don't have to write that. So we're starting with 4.5 meters, and we're trying to get to centimeters. Now, even though you think you could do this problem in your head or just scribble down a quick calculation, you want to learn to set the problems up the way I'm about to show you here, and it's going to be required. That's really what I'm looking for, because believe me, you will quickly get into chemistry problems that you can't just do in your head. And so what you do in this is you let the units of measure guide you on how to set up the problem. So let's go to this. So the relationship between meters and centimeters is 100 centimeters equals 1 meter. This can be expressed as 2 conversion factors. 1 meter for 100 centimeters or 100 centimeters for every 1 meter. The question mark means that we must choose which of these two ratios to use. Only one will work in this problem. So again, they're both true statements, but which one are we going to choose? So think about it. We need to make meters disappear, cancel out because it doesn't appear in the final answer, and we want centimeters to appear in the final answer. That means we're going to need meters in the denominator and centimeters in the numerator. So we go ahead and take that one of the two. Again, the other one's true, but it doesn't help us in this problem. So there you go. So you have 4.5 meters times 100 centimeters over 1 meter. So now I'm just going to rewrite it again here. And now we can cancel. We have meters in the 4.5 meters. We have meters in the numerator, and the 1 meter on the bottom, we have meters in the denominator. So meters over meters cancels. The last man standing is the centimeters. So once you have your units lined up so that they cancel properly and you end up with the proper unit that you're looking for in the final answer, then you do the math. So it's going to be 4.5 times 100 divided by 1, and that will give you 450. All right. So this is one of the most important skills you're going to learn in chemistry, is how to set up equations like this and how to work the equations like this. Okay, so here are some of the most common basic units of measurement in chemistry. Grams is the amount of matter in an object. It's a measure of mass. In chemistry, we can use the words mass and weight almost interchangeably. You can't do that in physics class, but here we can treat them as though they're the same thing. But generally, it's proper to say grams is a measure of mass, not a measure of weight. Liters is a measure of volume. How much space does something take up? You've probably all bought a 1 liter bottle of soda or of water, so you know about how big a liter is. Meter is a measure of length. Okay, in track they run a 100-meter dash. So that's something that you might be familiar with, or some other measure that's in meters. If it's square meters, meters times meters, it becomes area. It's amount of area, surface area, like the square meters of our classroom. And cubic meters would be meters times meters times meters. That would be a measure of volume. That's something in 3 dimensions. Time. A second, minute, hour. Those are common throughout the world. It doesn't matter what system of measurement you're using. There are 2. One is the English or imperial system that we use here in the United States, and the other is the metric system, which is used in most other countries of the world, except for just a very few. And it's also used in science. We will pretty much never use English or imperial units like feet, yards, miles, inches. We won't use those in our class. But seconds, minutes, and hours are universal. Temperature can either be measured in degrees centigrade or kelvins. And joules is the standard unit of measure for all forms of energy. That would include mechanical energy, when you throw a ball in the air, heat energy, electrical energy, light wave energy. We will talk about it in that context. So those are the base units of measure that we will be using in class. The prefixes, words that come before, can be placed in front of a unit of measure to assign a number value. So here's a big long chart of these. So if you let's use the example of meters. If you said megameters, that would be capital M is the abbreviation, and 10 to the 6th is the power. So if I said 2 megameters, that would be 2 times 10 to the 6th. By the way, we're going to talk about scientific notation coming up here. The ones that we'll use the most in this class are giga for 1 billion, mega for 1 million, and kilo for 1,000. Hecto we never use, deca we never use. Deci, which is 1/10 of a meter, is rarely used, but we will use frequently centimeter, millimeter, micrometer, nanometer. Okay, and I'm using meter as an example. It could be grams. It could be nanograms, micrograms, milligrams. In other words, these are prefixes that can go in front of any of the units of measure that you saw on the previous slide. So we'll practice this because it does take a little bit of practice. Okay, so prefixes such as mu, that looks like a U with a little leg on it there, N for nano, K for kilo, in front of the unit of measure indicates the power of 10 to be multiplied by the number in front. So here are some examples. And you do have a copy of that previous slide in your reference sheet section. So if you have 6.7 micrograms, that means 6.7 times 10 to the minus 6. Go back to that chart on the previous slide. 6.7 times 10 to the minus 6 grams. If you have 430 nanometers, nano is 10 to the minus 9th, so that's 430 times 10 to the minus 9th meters. 230 kilojoules, that would be 230, kilo is 10 to the third, so 230 times 10 to the third joules. Again, you'll get used to using these very quickly by just using them, by just working problems with them. At first, you might have to think about them a little bit, but eventually they'll become just as natural as counting 1, 2, 3, 4, 5. Scientific notation is a way to convert very large or very small numbers to a shortened length. And believe me, we use some very large and very small numbers in chemistry. So much of chemistry is done in scientific notation. Again, it's just something that you get used to. It's not that hard, and it just, with practice, as you do problems, it'll just come naturally to you. So example, the speed of light is 300 million meters per second. In scientific notation, it is 3 times 10 to the 8th meters per second. That's 300 million in scientific notation. So you can see it's a bit shorter to write 3 times 10 to the 8th meters per second than it is to write a 3 with all those zeros behind it. So the parts of scientific notation number are the coefficient, the base, and we always use base 10 in scientific notation, and the exponent. Converting from decimal to scientific notation, 46,700. The comma is for readability only and can be removed. So you place the decimal at the end of the number. So in the United States, a comma simply makes a big number easier to read. In some countries, the comma is treated like a decimal. In some countries, that would be read 46.700. It would be a totally different number than 46,700. But in the United States, the comma doesn't mean anything. It's just meant to make the number a little bit easier to read. So we're going to take that comma out and we're going to put a decimal at the end. Now you move the decimal to form a number between 1 and 9.999. You count the number of positions the decimal was moved. So there we go. And there you can see we had to move the decimal over to be in between the 4 and the 6. So that 4.67 is a number between 1 and 9.999. And we had to move it 4 places. The decimal was moved 4 places, and the original number is greater than 1. 46,700 is the original number, was greater than 1. So that means the exponent is positive 4. If the original number is greater than 1, then the exponent is going to be positive. So what we then have is 4.67 times 10 to the 4th power. 10 to the 4th power is 10,000. 4.67 times 10,000 gives you 46,700. Okay, converting from decimal to scientific notation. Okay, so here's another example. Now you notice this is a number less than 1, but it's a positive number. So what we're going to do is move the decimal to form a number between 1 and 9.999, count the number of positions the decimal was moved. So you moved it over in between the 8 and the 2. That's a number between 1 and 9.999. So that's 3 positions. The decimal was moved 3 places, and the original number is a number less than 1. So that means the exponent is going to be a negative 3. So the scientific notation would be 8.2 times 10 to the minus 3. So note, a negative exponent does not mean a negative number. It is a positive number between 0 and 1. Now let's go in the other direction. Let's convert from scientific notation to decimal. So here's a scientific notation number. And what you do is you write the coefficient by itself and move the decimal the number of places of the exponent and fill the blank spaces with zeros. So we're going to write 6.7 by itself, and then you're going to move the decimal 3 places. Now, how did you know it should go in that direction? It could have gone in the other direction. The exponent is positive, so the number will be greater than 1. That means you need to move the decimal in the direction that will make it a number greater than 6.7, and that would be moving the decimal to the right. So you just kind of use your common sense about that. You can see that 6.7 times 10 to the third is going to be a number much bigger than 6.7, so you're going to have to move the decimal to the right. and that number would be 6,700. And the decimal can be eliminated if there are no digits to the right of it. Okay, so that would be the answer for that. Okay, let's try another one. Try to do this one on your own. It's got a negative exponent this time. So you write the coefficient by itself and move the decimal, the number of places of the exponent, and fill the blank spaces with zeros. So this time it's a negative 4. That means it's going to be a number less than 1. So to make 2.1 become a number less than 1, you're going to have to move the decimal to the left. So we move the decimal to the left 4 places, and you end up with 0.00021. And the exponent is negative, so this is a number between 0 and 1. It's a positive number, but it's between 0 and 1. And that's your final answer. A leading zero should be placed to the left of the decimal. That's just done as a matter of convention. So yes, you should always do that, but it doesn't change the value of the number. It still has the same value. Okay, now we're going to multiply scientific notation numbers. Multiply the coefficients and add the exponents. So you multiply, in this case, 4.1 times 1.8, and you add 7 plus negative 2. That's the way you could read that, or 7 minus 2. That would give you 7.4 times 10 to the 5th. Now, when one of the numbers is scientific notation and one of them is not, you simply multiply the one that is not by the coefficient only. So 3.6 times 2.3. So multiply the decimal number with the coefficient of the scientific notation number and adjust the exponent if necessary. We're going to talk about adjusting the decimal if necessary. Okay, so 3.6 times 2.3, that gives you 8.3, and then you didn't change the scientific notation number. It's still 10 to the minus 6. We did not need to adjust the decimal or the coefficient. The decimal or the exponent, but you're going to see that coming up here pretty soon. So we're going to multiply these two numbers here. Multiply the coefficients and add the exponents. So 5.200 times 2.300 is going to give you 11.96, and then you add the 3 and the 2 in the exponents, and that gives you 10 to the 5th. Now, that's your answer. However, it is not a number, 11.96 is not a number between 1 and 9.999. So what you need to do is adjust the decimal and the exponent. So the decimal must be adjusted in this answer so that the coefficient is a number between 1 and 9.999. So what we're going to do is move the decimal over one place to the left and turn 11.96 into 1.196. But just doing that would change the value of the number. We don't want to do that. So what we're going to then do is increase the exponent from 5 to 6. So 11.96 times 10 to the 5th is the same value as 1.196 times 10 to the 6th. Here's the reasoning here. The way you reason it out is you made the coefficient smaller. You went from 11.96 to 1.196, so you have to make the exponent bigger to offset that. So those two numbers remain the same. Another way to think of it is you took 11.96 and divided by 10 to get to 1.196. So what you did with the exponent is you multiplied by 10. 10 to the 5th and 10 to the 6th is a multiplication of 10. 10 to the 5th times 10 is 10 to the 6th. Anytime you increase the exponent by 1, you're increasing it by 10 times. So you divided the coefficient by 10, and you multiplied the exponent, the base and the exponent, by 10, so they offset each other, and so those two numbers are of the same value. Move the decimal to the left on the 11.96, making it 1.196. Then the exponent becomes bigger from 5 to 6. The coefficient has been made smaller by one place, so the exponent must be made bigger by one place. That's the way to think of it. The two numbers above have the same value. If you make the coefficient bigger, then the exponent must be smaller. If the coefficient is made smaller, then the exponent must be made bigger. Okay, now we're going to divide fractions. Divide scientific notation fraction. So divide the coefficients and subtract the exponent. So 5.2 divided by 2.5 and 6 minus 2. So there's no decimal adjustment is needed here. So 5.2 divided by 2.5 is 2.1. That's a number between 1 and 9.999, so we don't need to adjust the decimal. And 6 minus 2 is 4. So that's how you would divide scientific notation numbers. Okay, adding or subtracting scientific notation numbers requires a common base and exponent. You won't do this very much in this class, if at all. But here we have 5 times 10 to the third plus 3.7 times 10 to the fourth. You can't add those two numbers because you have a 10 to the third and a 10 to the fourth. You have to get the same base and exponent. Now you could either turn the 10 to the fourth into a 10 to the third or the 10 to the third into a 10 to the fourth. That's what we're actually going to do, is that second one. So a common base and exponent can be created by moving the decimal to the left on the 5, making it 0.5, 0.5. Then the exponent increases from 3 to 4. So we went from 5 to 0.5. So we made that number smaller. Going from 5 to 0.5 makes that number smaller, so we offset that by making the exponent bigger by 1, 3 to 4. So now you see down there you have 10 to the fourth in both of those two scientific notation numbers. Now you can add the coefficients. So 0.5 times 10 to the fourth plus 3.7 times 10 to the fourth equals 4.2 times 10 to the fourth. And that's it. So this is some of the math that you will get good at very quickly if you do all of your assignments. I'll give you some practice problems on this. And we will continue on with a little bit more math for chemistry in the next lesson.